Okay, thanks everyone for coming along to this session. Following on from my presentation this morning, I'm hoping that we can take a bit of a deeper dive into a few of the core materials we engage with as building professionals. So that's materials that can impact heavily on this climate and biodiversity crisis that I keep banging on about. And how might we do things better with our material specifications? So, as also David mentioned just before lunch, the World Green Building Council has put the built environment as responsible for 39% of total global greenhouse gas emissions. And if you add to that, the biodiversity decline that's attached to both the procurement of building materials and the commandeering of previous natural ecosystems to locate our built environments, it becomes pretty clear that we building professionals are key accomplices to the crisis that we've got. But that said, we can also be key drivers for urgent, environmentally and socially regenerative change. And it's why there are now hundreds of thousands of Australians engaged in the future of built environments who, in one way or another, have mobilised to address this emergency head-on. They're changing the way they design, specify materials, innovate and advocate in the community and to the powers that be. So without a doubt, this focus is where our broader social gaze is rapidly shifting. It's where business can prosper, and it's the only way forward by which our finite and precious planet can continue to support our civilisation as we know it. So there are three main prongs to how we built environment workers, what we can do in tackling this crisis. Firstly, we can address the operational impacts of buildings, so their energy demands in heating, cooling, lighting, that sort of thing, as well as their water consumption. And that's been the main focus to date, certainly with building codes, as they ramp up the minimum thermal performance of building envelopes, as well as the energy and the water efficiency of fixtures and appliances. Secondly, we really ought to look more closely at the environmental impacts embodied in the construction of buildings, and that's mainly bound up in materials. Thirdly, and most critically, we need to address the amount or scale of building that we think we need. And this has the most significant impact on the first and the second prongs, but for a bunch of reasons, we in our industry don't really want to talk about it. All the codes, green building standards, and even design awards, they're couched on the basis of impact reduction per square metre of floor area, instead of per occupant, which is how it should be measured. It's a key flaw in sustainability mantra around our built environment. If we don't quickly face this in Australia, we'll soon be pariahs in the global community, deeply suffering the impacts of climate and biodiversity collapse. So you can see, again, we're the top of all the countries in the world. Though not per occupant, but per square metre of floor area, the operational energy and water efficiency of buildings in Australia, it's slowly improving. But what that means is that the materials used to construct them remain as the primary driver to their overall life cycle environmental impact. So building services and appliances that are attached to the operation of buildings, they can be upgraded, and you see that through the life of buildings even now. And that's to embrace new technologies and to provide improved energy and water efficiencies through what needs to be a very long service life for a building these days, because we just don't have the resources to to just pull down and redo our built environment. But our specification of concrete and steel and bricks and wood drives more serious environmental impacts and carbon emissions that are locked in, and they're irreversible the day our job goes out to tender. It's an awful inheritance for younger generations by way of natural resource depletion, biodiversity loss, and of course, crippling climate change. Now, there are tools available to model life cycle environmental impacts, so embodied and operational impacts in carbon emissions, water use, toxicity, ecosystem degradation from cradle to grave. There might be some terrific tools out there, but those I've engaged with, they tend to draw on inflexible assumptions about the future, and then in address of materials procured for a build, LCAs reference environmental product declarations. And EPDs, they can also rely on problematic assumptions, at least as I've found it, and they lack the detail that's required to compare performance of a product type across the available supply chains. I think as designers we need and deserve to know that. I've also found the analyses and the reports that are generated from life cycle impact modelling, they tend to provide little design guidance for us, considering the time and the money that goes into them, especially for small projects. But that said, I've not worked with LCAs these last couple of years, and I trust they're getting smarter and more helpful for designers. In the meantime, we're pretty safe to assume that cement and concrete, fired clay, steel and timber products are likely to be the most impacting materials to find their way into our builds as they rise from the ground. And why is that? It's because these are the materials that we use the most of by volume in building construction. It's also because the manufacture of steel, cement and fired clay products in particular requires a heap of heat energy, the vast bulk of which is derived from fossil fuels. And there's not much underway yet in these industries to transition to renewables. And the procurement of timber products draws on living forest systems in ways that can but need not impact badly on their further prospects, these forests, for carbon storage, atmospheric CO2 sequestration, and for their biological health. So let's march for climate action, definitely, but also let's look at some other easy implementable actions where we can really make a powerful and an immediate difference in our workplace with our building designs and our material specifications. So let's start with cement and concrete. Alone Portland cement, which I introduced a bit this morning, which binds, everyone here knows, binds the stone and the sand in concrete, but just the cement, that accounts for a whopping 8% of the planet's total greenhouse gas emissions. So roughly the same as the entire transport sector, just in cement manufacture. In the rotary kiln, that's up sort of on the top image there, the fiery orange part, that's where the coal and or gas are burnt to produce clinker from crushed limestone. So 32% of carbon dioxide attached to cement manufacture is emitted in that spot. A further 55% of these emissions are attached to the chemical reaction that takes place under this kiln heat when limestone, calcium carbonate, is converted to lime or calcium oxide and carbon dioxide. So even once we've fully transitioned to renewable energies for manufacturing cement, the bulk of its emissions, 55%, will remain impossible to avoid while it's based on calcination of limestone. We need to quickly move away from these lime-based or Portland cement binders for concrete and for mortar. Thankfully, there are other equally effective and readily available concrete binders, such as fly ash, which is a waste from coal-fired power generation, and slag, which is a byproduct from steel smelting. The Romans used volcanic ash as a concrete binder to build the Colosseum, and it's still standing, kind of. These alternative binders are collectively referred to as supplementary cementitious materials, or SCMs, and the environmental impacts attached to their manufacture are very, very much less than for Portland cement. across that Mullum Creek eco-housing estate, which I spoke about this morning, we required that SCMs make up a minimum 30% of the cement that was used in wet mix concrete. Some designers and engineers, they chose to increase that to up around 60% where surface finish wasn't critical. So for things like in-ground piers, strip footings, retaining walls, that sort of thing. Initial resistance to SCMs, it really subsided on that project as the concreters found that ground slabs containing SCMs were stronger and with less shrinkage cracking. And as the bricklayers realised that bagged cement containing 50% SCM was equivalent to general purpose Portland cement in availability, performance and price for the mortar they were mixing. And the rammed earth contractors, they found that slag, so that waste from steel smelting, performs quite well as a cementitious material without reducing those nice earthy wall colours to a drab grey. Today, whilst some local concrete batching plants push environmental innovation more energetically than others, pretty well all are happy to supply concrete with SCMs with no increase to supply cost at all. And they're now also available in most regional centres and some rural towns, certainly in Victoria. Some of them are also willing to add crushed recycled concrete in with the aggregate mix, certainly the ones in the city. And you can use that for those lower strength applications like board piers, sub-base and blinding concrete. These days we're going further and further afield to source virgin rock and sand for concrete. So the sand can't be weathered or rounded in the way beach sand or desert sands are. It needs to be angular to create that good structural matrix. And so it's surface mined from recent sedimentary deposits that lie beneath often delicate natural landscapes. Globally, it's acknowledged that we will soon simply run out of virgin angular sand. So research and development for recycling our gigantic hard waste streams to produce both coarse and fine concrete aggregate, that needs to ramp up urgently. And when it does, we building professionals need to promptly preference these recycled aggregates as we need to preference SCM concrete as it's available. SCM mixes are now finding their way into large public buildings and infrastructure projects, and that's partly, I'm expecting, because of the Green Star status that many of these jobs are chasing, and that's really terrific. But contractors laying concrete for private residential and commercial slabs and pavements, so the guys I'm expecting many of you will be engaging with, they're less likely to order these environmental mixes unless you drive that from your position as designers. So towards substantially reducing the carbon footprint embedded in your designs with a no-cost, no-brainer, I really strongly encourage you to insist that your engineer specifies concrete with SCMs replacing Portland cement in the highest proportion that's appropriate for a given application. And then to give these specifications teeth, if you can monitor compliance by requiring the builder to gather and copy back to you all concrete delivery dockets, that'll confirm what's in the mix. Bagged cement with high SCM content is also readily available. Let your brickies know why you need them to use it. And once they've opened the bag, they'll struggle to pick the difference. That's what the brickies have said to me. And here are some links on the Mullum Creek website to guide you some more on cement and concrete. Fired clay bricks, they're back in vogue, certainly amongst architects. Like cement manufacture, the firing of clay bricks and roof tiles requires even huger amounts of heat. There's Austral Bricks have a brick-making plant at Longford in Tasmania that uses mostly sawdust to fire its kilns. But to my knowledge, apart from the relatively small quantity of bricks that are produced there, we're looking across Australia at around 660 megajoules of gas to produce solid fired clay bricks for 1 square metre of single skin brickwork. And that compares to only, well, it's still a lot, but only 240 megajoules for solid single skin concrete blockwork. So not even hollow, solid. In this emergency, these industries that rely on heaps of gas or coal and super high temperatures to manufacture their building materials, they're for the most not transitioning to genuine renewable energy sources anywhere near fast enough. As a genuine renewable, I include bioenergy only if it took little over a year to grow and harvest, also with minimal irrigation or fertiliser input, or if it's an industrial waste product. Without carbon capture and storage, even the burning of sawmill waste at the Longford kilns is problematic in this emergency. So while we wait on much more environmentally benign technology for firing clay bricks and roof tiles, we're best to look to recycled bricks or other cladding materials where we can, I think, and require our tradies to lay every brick in a pliable composition mortar, not a sort of a much more brittle cement mortar, that allows it to be more easily cleaned and reused from one project to the other when one building has finished its life. And we might want to look once again to earth bricks. They're currently not in vogue. But with climate-conscious architectural detail and good QA in manufacture, sun-baked mud bricks and ram-pressed earth bricks can be laid as tall and as weather-resistant as rammed earth and other masonry and monolithic wall systems, fired clay bricks, tilt slab panels of concrete. We could easily refine this very simple, environmentally benign and socially inclusive construction method for a 21st century revival. These photos are from one of the several community self-build projects that had me living and working up north through the 1980s and 1990s. Here's a link on the Mullum Creek website that'll guide you some more to those on clay products. And what about steel? We're told that the manufacture of steel accounts for another crazy 8% of our total anthropogenic emissions. Now, I think there's nothing wrong with a sheet of corrugated iron. Coated steel wall and roof cladding provides an expanse of robust and almost maintenance-free cover that's difficult to surpass at less than 0.5 millimetre of material thickness. But per unit volume, the carbon footprint of steel is staggeringly high compared to all other common building materials, even including aluminium. And you can see here how per square metre of product, 9 millimetre thick fibre cement sheet has an embodied energy significantly below that of only 0.5 millimetre thick steel sheet. And check out the embodied energy in just 2 sheets of light SL82 steel reinforcing mesh for a 120 thick concrete slab on ground. It's about the same as the embodied energy in the concrete itself. So here it's 20 MPa concrete with only Portland cement as its binder. When 40% of the Portland cement is substituted with SCMs, this light steel reinforcement ends up having the greater carbon footprint in that element. Over my working life, the tensile strength of concrete reinforcement, that steel, has increased from 250 to 400 MPa, and that's reduced the volume of steel required, which is great. But by volumetric measure, you can see here the extraordinary carbon footprint of today's virgin steel that's smelted from iron ore under extreme coal-fired heat. So reducing the amount of weighty steel in construction is one of the best things we can do to minimise embodied carbon. In too many simple structures, I see steel used where substitution with a responsibly sourced timber would have been another cost-saving no-brainer. The Mullum Creek Design Guidelines were formalised with a requirement prohibiting the use of cold-formed steel framing, so that, the stud framing that was David showed. But the use of hot-rolled steel we permitted. And I learned a few years later, after we'd finalised the design guidelines, that Currumbin Eco-Village in Queensland prohibited hot-rolled steel without much kickback from designers or builders. So in hindsight, I reckon we could have done that too at Mullen Creek. Nonetheless, this guide from Mullen Creek, it lists steel products that are manufactured locally and comparatively energy efficient ISO accredited processes to do it. We've got design eco-warriors in our midst who argue that steel is fully recyclable and so it's the ultimate framing material. When the day comes that global industry draws solely from recycled steel stock and renewable energy for its resmelting, I might look to agree with them. But until then, and it looks to be a way off, this climate and biodiversity emergency must have us desperately looking to where we can reduce the amount of structural steel that we shove into our builds. We need to start questioning architecture on our drawing boards that relies on lots of highly reinforced concrete and hot-rolled steel just to stand up. We need to ask ourselves why such structurally demanding designs are even necessary. Are we chasing building heights that are simply unsustainable, also by social measure? Has our architectural flair for gravity-defying cantilevers overtaken our responsibility to design light and lean in response to the crisis we've got? What other less impacting materials could we use for our structures? Well, what about wood? And this is where it might get a bit controversial because we've had some really different the takes here on today on timber, and I'm just calling it the way I understand it after many, many years of working with wood and doing lots of research and talking to people in all sides of the industry. The recent 6th assessment report of the Intergovernmental Panel on Climate Change, or the IPCC, it references the world's forests many hundreds of times, not only for their ability to sequester atmospheric CO2, which we heard about this morning, but also because they're crucial holds of biodiversity and carbon, and so seriously threatened by wildfire, heat-related dieback and other decline, which is occurring in our native forests big time now, impacting on and being impacted by climate change in what's a frightening feedback loop. So in this infographic, you'll see that boreal, so those northern hemisphere cold climate forests, tropical forests and temperate climate forests are the land systems with the densest above-ground carbon storage. The coloured land areas here, they show the world's forests. So up the top, that great big band right across the planet of all that green and other colours, they're those boreal forests. The hot climate wet tropical forests of Central Africa, the Amazon, of course, Southeast Asia, PNG, and the temperate climate forests, so the eastern seaboard of Australia, a little bit in Western Australia, parts of China, western side of the USA, that temperate climate forests. Deforestation of the northern hemisphere's boreal forests. They're the largest terrestrial, that being the largest terrestrial biome on the planet. That'll have catastrophic impact on our global climate if it continues at the rate it has. It's true that much clearing of tropical forests is done to win agricultural land for grazing and for cropping. But certainly, much of the wood used for building construction in Australia is sourced in ways that damage the crucial ecological values and the climate stability that natural forests provide. So you'll see, make it wood and it's the ultimate renewable. The truth of the matter is that timber can be a very good or a very bad material to build with, and it depends all on where and how it's sourced. So let's start with structural timbers because that's where most wood in buildings tends to go. Those very slow-growing cold climate boreal forests are where much of our simply sawn framing wood in Australia comes from these days. And anecdotally, it seems to me somewhere between 15 and 50%, depending on global market flows, certainly in Victoria. Our local pine and this imported spruce are stacked together on the racks in your timber yard. No labelling to differentiate them, same price. But check the end grain and it'll tell you the story. So on the left top, you'll see there's about anywhere between 5 and 9 years of growth in a stick of that stick of 90 by 35 framing pine. On the bottom at the right, I can count around about 29 to 30 years across that 35, but you'll see it through the whole timber, there are some 100 years of growth. So each ring is a year in the growth of a tree, certainly in the colder climate and temperate climates, a bit different in tropical areas. This tells me that forest carbon debt incurred if we use slow-grown boreal forest pine will take 4 to 8 times longer to repay or return back to nature than if we use fast-grown local plantation pine. So something like 80 to 200 years instead of 25 to 30 years. And in the time that we've got left for impactful global climate action, that's a problem. So I really encourage you, if you can, insist that your builders order timber grown locally in Australia in the warmer climates. At Mullum Creek, we did that. We did very regular checks on site, and we tried to, if there was a problem, we tried to catch it before they unpacked the pack, because often it wasn't the builders who made the mistake. It was actually at the timber yard where the mistake was made. The same applies to engineered timber products. Like most of the laminated veneer or LVL in our builds, virtually all that you saw this morning on the mass timber construction there, all that timber came from the other side of the planet. Much faster grown and locally engineered softwoods have dramatically lost market share in recent years. But I encourage you to insist that your engineer specifies and your builder orders these by brand, these engineered products, as they're available in your state. The same applies to most of our structural panel bracing. Oriented strand board, OSB, is all from northern boreal forests. Those darker red and very thin plywood that you see bracing on walls, they're hardwood species from Southeast Asian tropical forests. You see that on the left. Please have your engineer specify local, fast-grown plantation pine plywoods for structural panel bracing, so the one you can see in the middle of that image on the left. And it wants to be branded, so you can see that it is an Australian product. Again, the same for most of our cross-laminated timber and much of our glue-laminated timber, also sourced from these cold climate forests on the other side of the planet. But we do have CLT fabricators working with local fast-grown plantation pine. So there's Xlam at Albury and Crosslam in Perth. Here on the top right of that screen is shining gum in a Tasmanian plantation. Originally it was planted on bare farmland for the fickle wood chip industry for pulp, and it's now ready for harvest after only 15 years of growth. There's a company called Cusp at Wynyard is processing it into high-value glulam beams, CLT panels, and I hope soon also window joinery timbers. So there's no natural forest carbon debt here at all. Please support Xlam and Crosslam, Cusp, and other companies like that as they emerge to do that in your work. Timber engineering is an excellent space for small-scale local enterprise to thrive, making the best use of these super fast-grown but immature plantation woods that we'll need to look to until we have this climate crisis sorted. And meanwhile, we can preserve our natural forests for the many other precious ecological services that they provide. And by sourcing timbers responsibly, we're sending a clear message to forest and timber industry that we will accept nothing less for the sake of our children. So I encourage you to keep this simple guide handy and let it inform your specifications. It's a green light and a red light list of structural timbers that are available in Australia. It's regularly updated and lives on both the Mullum Creek and My Office websites. Insist on locally fast-grown plantation woods as they're listed here. There's no need whatsoever to specify imported or Australian native solid sawn forest timbers for structural applications. As many of you will know, the tropical rainforests of Southeast Asia and the Amazon are where many of our great Aussie decks come from. Certainly all those that are built in Merbau or Coormaroo, and increasingly also some of the other durable and stable timbers that we want for our external building applications. So Manilkara, New Guinea rosewood, those sorts of things. And gosh, even the spit roast charcoal at my local servo, it comes from really quite ecologically crucial mangrove forests of Thailand. So please avoid these tropical forest woods. If your project's in Victoria, you can support Ceres through its not-for-profit aggregator, Fairwood, which I spoke about this morning. You can check out their naturally durable farm-grown sugar gum. Their macrocarpa and blue gum, all grown in plantation on farm for external applications. Thermally modified LOSP and ACQ treated plantation pine decking is widely available, also in knot-free grades if that's an aesthetic consideration. A lot of people seem to be put off by the knots in pine, but they do grow clear and select grade pines, and most of that comes actually either from Queensland and certainly a lot from New Zealand. So Obodo from New Zealand and Hine, Queensland, make a really smart decking of this kind. And most of my clients' decks, they end up weathering to a grey anyway. And then there's not much of a difference in the look of the clear grade pine and the native Australian hardwoods. They're also cheaper, the plantation wood. This Mullum Creek info sheet, it'll help you to work out what all the numbers on those little tags on the treated pine mean in terms of chemical toxicity. So copper, chrome, arsenate, or CCA is obviously the treatment you want to avoid. If your clients are comfortable with composite wood plastic decking, Modwood is manufactured in Melbourne from local plantation pine sawmill waste and recycled PVC milk bottles. It's also available in Bell 40 bushfire resistance. Other wood plastic deckings are best avoided because they're manufactured mostly in countries where OH&S around volatile plastics is poor, and they also often draw on virgin forest and petrochemical resources. And what about timber from Australia's native forests? This is where a lot of people become quite emotional around. Deforestation is still happening across Australia, but it's occurring mostly in the relatively sparsely vegetated, dry open woodlands and savanna country of southern Western Australia, inland New South Wales, Queensland and the NT's top end. It's a very different landscape to the tall, wet and dry sclerophyll forests from where we source our timber and our pulp, but the timber for construction. By comparison, these tall forests are not at all expansive, but they hold most of our country's forest biodiversity and certainly most of our forest carbon. So our tall, dry sclerophyll forests, they're particularly vulnerable to catastrophic bushfire, as we know, and the frequency and the severity of which have ramped up substantially with the hotter and the drier summers that climate change is serving us up. The tall, wet sclerophyll forests are slightly less vulnerable, at least for now, to this frequent cataclysmic wildfire. But they are by far the most broadly impacted by logging for timber and pulp. And they're the forest types we need to focus on, because that's where our wood's coming from. Tall wet forests of Victoria's Central Highlands, just north of here, store more carbon per hectare than any other terrestrial ecosystem on the planet. They're also the forests from where most of our mountain ash and alpine ash are sourced, and they're probably the native hardwood timbers most widely used in architecture across Australia. According to the University of Melbourne's Professor Patrick Baker, even more so than wildfire, broad-scale and intensive logging practice, as you can see here, it reduces the regenerating forest to a mostly singular and immature age class that'll for the most not produce quality saw logs in its 60 to 80 year harvest cycle, certainly not the next 60 to 80. It won't accrue as much forest carbon post-harvest. It won't recover well as a biodiverse ecosystem in the aftermath of inevitably more frequent and severe bushfires that we've got ahead. And there's also little underway in forest management practice between the harvest cycles to improve the quality of the timber yield or the prognosis of this natural ecological system, which together with the world's other tall forests will be crucial to our very existence in a future stressed by greater heat and summer droughts. Now, the heart of the problem here, as I understand it, is not the practice of clear-cut logging per se, but rather the pace, the sheer scale and the intensity of it across tall forest landscapes of Australia. Without clear evidence on the ground of truly transformative change to the management of production forests and some equally clear messaging about the same, I can't see native forest logging continuing in most Australian states for much longer at all. Alone, the shifting socio-political sentiment simply won't allow it. The claim that building with wood is good because it locks up carbon sequestered in a tree, I would say that is flawed in the context of native forest logging practice in Australia and other countries, as it occurs for the most in the time frame of this climate emergency. So around 50% of the carbon or the biomass that was stored in this native forest mid-last year has now been pushed into a windrow and it's been burnt, 50%. The few retained seed trees you can see there, they will have almost certainly died as a result of the post-harvest regeneration burn, or they'll soon succumb to increased exposure that they've not grown up to face. Of the logs that are removed from the site, only around 20% are of sawlog quality. The yield from these sawlogs, first to rough sawn hardwood, then via kiln drying and machining to product that's going to be ready for the building site, that'll be in the order of 30%. If you lose another, say, 10% on the building site to construction, some offcuts, wastage, then you're left with only 3%, give or take, of the forest carbon debt incurred last year, locked up in construction this year from that site. Natural forest regrowth here is going to take 90 years to repay that full carbon debt. And that assumes the forest suffers no bushfires damage between now and then, and that the heat and the drought through those 90 years won't be worse than it was in the last 90. The science tells us that's very unlikely. And this debt repayment involves a time frame way beyond what we have left for impactful global carbon drawdown. Australia and New Zealand have expansive plantations of exotic pine, and they do provide for a good part of our construction softwood needs. Again, both simply sawn and to a lesser extent, Australian-made engineered product. But here, we've been loath to expand our plantation estate in Australia, which since 2006 can only happen on historically cleared land. And we're not doing that because of the long time frames and the investment risk attached to this business at the vast scale it likes to operate at. It's much easier and safer, it seems, for the man at the timber yard to make a phone call overseas to one of the big processors of Baltic or spruce from those natural boreal forests of the Northern Hemisphere. And by way of plantation hardwood for timber production, we've had ridiculously little happening in Australia over recent decades. We desperately need a dramatic increase in new plantings across the rural landscape of both locally indigenous, native and exotic tree species on farm properties. Also in patchwork arrangements with green fire breaks to help protect against progression of megafires through the landscape. So these can be trees that are grown on farms for conservation and for profit. At Jigsaw Farms in Western Victoria, they're really going for it there. And across the agriculturally difficult, steeper slopes of South Gippsland, many small farmers are having a go. Growing some really valuable architectural wood. So timber from a web of small growers and sawmillers. So fair dinkum good wood that's then gathered and sold by the likes of Ceres Fair Wood, of which there could be many of those, again, across the country, repeated. So from my perspective as an architect, I'm confident that going forward, an increasing public and private client base will be keen to invest in and even pay a premium for wood that's produced locally from much more ecologically and climate-conscious forest and timber industry. I reckon these clients will embrace that objective with all building materials in the same way that they already have with energy and water efficiency, rooftop solar, those sorts of things. The responsible timber selection guides that we applied for Mullen Creek, and I spoke about this morning, they're freely available. They're commissioned by a family of environmental philanthropists, so you can be pretty sure that these guides are not influenced by commercial interests. They include a pretty comprehensive list of readily available timber products that meet quite stringent environmental and social criteria, and ones that are suited to all applications and budgets. And that list is regularly updated. Now, from my take here on responsible timber selection, you're excused for parking me in the camp on the left side of the screen. But by pressing pause on native forest logging, as WA and the Vic governments have committed to in 2024 and in 2030 respectively, we're also pressing pause on that noisy tussle for a simple fix, which is what big forest business and environmentalists fight for to prevail. I'm hoping that it'll allow us all to lend an ear to the likes of Patrick Baker, who I mentioned. He's from the School of Ecosystem and Forest Sciences at Melbourne Uni. Michelle Freeman, the Vice President of Forestry Australia, and Rowan Reid, who's a sage for every master tree grower on farm. They're advocating for transformative change to the management of all forests in Victoria, plantations, native production forests and conservation reserves, for a suite of smart silvicultural practices that do yield wood for construction, but first and foremost, make our forests more biologically diverse and abundant, as well as far more resilient to the increasing threats of climate change. On my office website, you can find a YouTube titled Local Enterprise with Trees and Timber, and it describes these experts' really balanced perspective in more detail, and I'm increasingly taken by it. And on the same web page is another YouTube that more methodically covers environmentally responsible timber choices for most structural, architectural and joinery applications. So it's a more detailed discussion on timber selection than I've got time to cover here. And finally, I want to stress the obvious, that responsibly selected materials, whatever they are, they won't make our designs and our constructions sustainable if they're not used frugally, if they're not sufficiently durable for a long service life, if they can't be easily disassembled for reuse at the end of that service life, and particularly if they produce buildings that are inflexible in their function and or beyond what we need for a modest life. Quickly to illustrate, just on designing lean with materials, For medium-rise construction, say 5 to 15 floors in height, cross-laminated timber from fast-grown plantation wood can make for carbon-friendly and material-efficient structural system. But for low and high-rise, where it also seems to now be the rage amongst architects, CLT is likely to be wasteful of precious wood resource. Here's a 2-storey home with essentially 2 homes worth of wood in it. So one house worth is in the CLT. Unfortunately, it's spruce. There's a house in Tasmania. And another is in stick framing, which also looks to be of spruce. It sits alongside the CLT to provide those cavities we need for thermal insulation and for services. If only the upper floor joists and the roof rafters were beefed up just a whisker, there'd be no structural and no thermal purpose to the CLT whatsoever. Sydney's 40-storey Atlassian headquarters, that'll be a hybrid timber tower. So it's going to have a concrete core, a steel exoskeleton, concrete 4 plates at 4-storey intervals, and with these 3 stories, so structurally you can consider them low-rise, inserts of CLT in between. In both these cases, the low and the high-rise, I can't understand why simple, conventional and material-efficient low and medium-rise timber frame construction systems can't be used. The argument that the more wood we shove into a build, the better, because it locks away atmospheric carbon, that's bolstered by a zero carbon building mantra, which, as I explained earlier, completely ignores forest carbon dynamics as they're most meaningful for the few decades we have left to impactfully fix the planet. I even hear CLT promoted as high-performing for passive house projects because of this thermal mass that they have. And yes, CLT does have some heat and cool storage capacity, but with the thermal conductance of pine, and most timbers, but pine very much, being only 12% that of brick and 9% that of concrete, and with interior shrouding of CLT behind insulation and surface cavities, a common thing, this thermal mass is unable to transfer heat effectively to and from the interior air. And a topic for another day. In all its functions, high-rise can never be ecologically or socially sustainable. This morning, I will have indicated that I like it when things are kept simple and local and joined with nature. And this afternoon, that I'm keen on techie things for a sustainable future. So before we go to questions, I can't resist but to finish with these guys from Wisconsin in the USA who fuse my passions with such grace.